I remember when latent or consistency models first came out, and they were kind of interesting. And then latent consistency models came out. They came out actually a while ago. I'm late on this one, um, and I think it's a cool idea. There was a paper I read earlier which kind of smoothed out the trajectory, but this does so in kind of a better way. It smooths out the diffusion trajectory in a better way. It also gives me a chance to talk about score models, which I don't really like talking about because it adds some complexities that are necessary to make a good diffusion model, but it also takes longer to talk about. But I do finally get a chance to talk about that, which is fun. So yeah, latent consistency models. I've been seeing them kind of been used with Stable Diffusion lately, so it's kind of cool. And I thought I would talk about them. The original diffusion consistency models came out with Dr. Sung, which basically did all the diffusion model stuff. I'm pretty sure it was Dr. Sung, and I'm surprised this wasn't. I guess he doesn't use latents very much. He likes the pixel base, but alternative to pixel base, this is the latent based approach, which is going to be better and more efficient. So to start off, we'll always do this. What is a basic diffusion model? Just for intuition. So a basic diffusion model, it is a text-to-image model, as you probably already know. And basically what you do is this is going to be the discretized trivial case. You take an image and you take an image and yeah, this is just our original image. We'll call this x0, and this is going to be t is equal to 0. So this is our original image. This is what we start off with. And basically what you're going to do is you're going to add a little bit of noise to it. So we will call this maybe, I think they call this p. I think it's p that adds a little bit of noise. And this will be x at time step 1. And this will be t is equal to 1. And then we do that again. And I didn't add the noise. So you add a little bit of noise. And this will be time step 1. And then you do this a second time. And this will be time step 2. So this will be x sub 2. And you just add a little bit of noise on top of that. And you keep on doing this over and over again using the same function. And you eventually end up with an image that is 100%, I do not like that. That is a 100% noise. And this is at time step t, big T, and yeah, big T. And that's usually 1,000. 1,000 is the basis. Everyone uses 1,000. And this is just all noise, like that. So you can model this as, say, x at time t is going to be equal to, we'll call this f of t x0 plus f of t z, or epsilon. We'll use epsilon, where epsilon is sampled from a Gaussian distribution, and we'll just say it has unit variance for ease. So yeah, that's how you model it, and you can think f at time 0 is equal to 1, or this is an f of t, it's 1 minus f of t, epsilon. So maybe at time 0 this is equal to 1, so it's 100% of your signal, your image, and then f of 1 is equal to, or f of t is equal to 0. So it's 100% noise and 0% image. Trivial case, but it gives good intuition. Now what you do, so this is p. Now you denoise this, you remove the noise using a model, and this model is just a unit. You basically give it an image and it produces a image with a little bit less noise. So you give it this image here at some time step, and it produces the image at a previous time step. So this will be, say, we'll call this epsilon theta. Epsilon theta. And you do this for all time steps. So basically you train this diffusion model for all 1,000 time steps so that it can reverse the process from anywhere along this chain. And epsilon theta is just modeled as it's just a unit, and you basically give it x at time t and some other stuff. Maybe you give it the text, so that would be some class conditioning. Maybe you give it some other modalities as well. but basically this is going to be equal to it's going to be equal to the noise at that time step. So this will be epsilon t. It'll just be all the noise. And then you can basically step your image by saying x at time t is equal to, or x at time t minus 1 is equal to x at time t minus some value, I'll just call this alpha, times epsilon theta of x at t and t. This is kind of like a one-step prediction, so it predicts all the noise in your image. It's not going to be super good at that, but you can basically take it's not going to be perfect, so you take like a small step in that direction. And this kind of looks like an Euler solver in a way, for a differential equation. And that's basically hinting that we actually use differential equations to model this. So this process here is the trivial case. If you discretize it, you just have this forward process that adds noise, and you have this backward process that is learned that removes noise. That's inefficient because you discretize it, and discretizing it, it doesn't get information of the entire trajectory. You want it to be a continuous process, and continuous processes usually work better in practice, just in general. So yeah, the idea is to make this a continuous process. So how do you do this? Now, if we look at, say, a normal differential equation, it would look like this, is equal to f of t dt. So simple differential equation, this is just like your change in x, change in t. So that's just a basic differential equation. Now, this isn't too interesting. Oh, I forgot the xt, xt dt. So yeah, this isn't very interesting, but yeah, that's the basis. And instead of that, because this is a deterministic process, so it's not that useful. Basically, if you have a point at time step 0, and you have a point at time step t, those points have a trajectory defining a path between those, and that path is going to be deterministic. And this process up here is not deterministic because we want to sample from it. You can sample from a deterministic process, but it's not really sampling at that point. So instead, we're going to use a stochastic differential equation. And this is defined as something similar to this. F of t and g of t are arbitrary. They define them as weird-looking functions that probably have some meaning in normal diffusion models. Diffusion models aren't actually a machine learning thing. It's just used. The diffusion process is just used in machine learning for this, but F and G are probably well-defined and using some crazy physics and math. It's a lot easier to simplify it, though. And this has the good old Wiener process here, or the Brownian motion. And basically what this is here is, well, you can't actually differentiate this, but if you discretize it, you can. And take a guess at what this term may be whenever you discretize it. And if you guessed Gaussian noise, you would be correct. Why would you use anything else? So yeah, whenever you discretize this becomes Gaussian noise, and it's similar to this equation up here, where basically you are defining, it's a differential in this case. It's a continuous differential, but you kind of have the two terms here, where this is your signal, and this is your noise term right here. This is your noise. So you have your signal and noise term, and that allows you to create this stochastic process, and that would be, this is basically your P. And it's basically saying like your change in x is equal to your current x, and you kind of just move it a little bit, but you also add a little bit of noise in that process. So it's just modeling the change in x with a little bit of noise in it. So what do these two things look like? Going back to good old differential equations class, it'll be good to look at for how you actually model this. So if we look at, I forget what this is actually called in differential equations, but it's the t versus xt plot. And basically you have x0 over here, and we'll define this trajectory x0 to x or xt like this. So this will be xt here. And you kind of have this flow, so there's actually like other trajectories here. And maybe it converges on some stable point up here somewhere. But the idea is that this is just an ODE. Basically, you have a point over here, and you define a trajectory from this point over here to this point over here, and that's that's basically you define this trajectory with your differential. And if we pick a point here, you basically have dx dt. So this is just your dx dt. So change in x, change in t, dx dt. And basically, if it's an ODE, this is easy to look at. How do you reverse this? So basically, like your forward process, it just as an ODE, so no noise added right now. Your deterministic process, if this is our original image here, this would be the cat image here. Then this would be the noise over here. Let's just say we model it as a single sample from a normal distribution, and it's always going to be that sample since it's not noisy. Then this is a deterministic process, and it's really easy to kind of map this. So this would be P. P goes from one area to the other, and you actually wouldn't need a model to predict this because you can just reverse the ODE, and that's pretty simple. You just go backwards. You just step backwards. And maybe this will be called, say, dx over dt hat, something like that. So yeah, this is your deterministic process. Now, a stochastic, on the other hand, looks different because you have noise. So this is xt, this is t, this is 0, and yeah, your stochastic, let's say we start in the same spot, x0, and this is the 1D case. So in this case, you're modeling a single pixel. Going beyond 1D is hard to visualize, but imagine your image is just a single pixel, and this is what we're modeling here. So the stochastic case would look something like this. So you start out here, and instead of going directly to a point, you kind of have this motion here defined if we discretize it. So this is kind of discretized, and each step is kind of just like this would be kind of your dt, and this would be your dx. I guess if we look at this one right here, then this would basically be your dt, and this would be your dx, and you add some noise there. So yeah. And you continue on until you land somewhere at time t. And you do this multiple times. So if I take the same exact sample at x0, then I get a different trajectory because the trajectory is noisy. So I get a different trajectory and it lands somewhere else. And I do this again, and it'll land somewhere else too. It'll land maybe up here. And all of these are x at time t, and we want to predict x at time 0. So we have all these x at time t's, and we want to get x at time 0. So these are all Gaussian noise. This is basically your Gaussian over here. This is your Gaussian. And basically you defined a mapping between the two, and it's a noisy mapping. It's from a deterministic sample to a Gaussian. And you may think to reverse this, so this is the forward process, that would be P. To reverse this, you can use an SDE. You can do that. That was how they originally did it. It's a lot easier to use an ODE. Once you already sampled the noise, you know you can just go straight here. So you know the trajectory you want to go in. Like once you've already, before you sample the noise, you don't know where you're going to go. Like if I'm right here, I don't know if I'm going to go all the way up here because I picked some weird sample from the Gaussian distribution, or maybe I go right here because I picked a different part of the Gaussian distribution. So I don't know where I'm going to go at any point. But once I have sampled from a Gaussian distribution, then I know where I was. So reversing it is deterministic. Going forward in time is not. So that means that we can train a model which is deterministic to reverse this process by just going over here to approximate this backwards trajectory. Song had a good, Song had a good, yeah, this is Dr. Song. Score-based generative models through stochastic differential equations by Dr. Song. And he had a really good image right here. And this image basically shows you have your data over here. And as you go forward in time, let me get out of this. As you go forward in time, you have this noisy process here. And this noisy process basically lands you somewhere on your Gaussian distribution. This is just your Gaussian. And then reversing the process, it can be deterministic, and it lands you somewhere back. So if I landed, say, right here, or we'll say right here on the distribution, right here, then you can reverse it by just going back to that point there. And I thought this was a cool visualization because it shows your data, and it shows the Gaussian, and it shows the mapping between the two. So that's the idea. You have this P, which is your noisy stochastic, and you reverse this with Q. And we'll get into that equation in a sec. So yeah, that's the idea. Those are that's ODEs and SDEs at a high level. So yeah, we would basically want to define an SDE as the forward process. So we want to define an SDE as a forward process, and that's just this right here. And you can think of maybe if we have the trivial case, f of t at time 0 is equal to 1, and f of t at time big T is equal to 0. So your change in basically your x is going to be 100%, basically 100% signal, 100% signal. So your change in signal is going to be at time 0, and then at time big T, you're going to have 0% signal, something like that. And then G, maybe at time 0, you basically have like very little variance. So something like this, you have like no variance. And then at time big T, you have a lot of variance. So at this point, it can go anywhere. I guess you can think of this as like a wider Gaussian distribution. If I'm like right here at this point, you have a large distribution for where you can kind of go. But at this point, you have a few kind of, you're more confined with the noise that it gives you. If you define this as, say, G of 0 is equal to 0, and G of big T is equal to 1. Now, this isn't actually how you do it. It's just, I think it's nice to see it kind of a trivial case of f and g. I remember when I first looked at this equation, I'm like, what is f and g? It looks a bit messy for what they actually are. If you want to see that right here, not as elegant. It's actually, yeah, they define it. They define it down there, but yeah, it's not as elegant. Oh, right here, yeah, they define it right here. And these are just your schedulers, alpha and sigma, and that's just defined by the normal distribution for how your data is kind of moving around. Yeah. Now, continuing on, we want to define a backwards process. So the forward process is pretty easy. It's just normal stochastics. Now, the backwards process uses something called score. So this is the score-based model. So your score-based model is saying your change in x, into your derivative at any time step is going to be equal to f of t xt. So basically your trajectory is going to be f of t xt minus 1/2 g squared t times s. So I'm just going to call this g instead. I think the 1/2 g squared t was some derivation that Dr. Song did in his paper. I'm not too worried about the exact formulation of g, just kind of the big idea. Now, s is our score, and the score is equal to this is the gradient of x, or the gradient with respect to x of log qt xt. And q sub t, is equal to, that's right here, basically your Gaussian, or your normal distribution, which has a mean of alpha t x0 and sigma squared t. So mean, variance, it's just normal distribution with different means and variances, just depending on how you want to define this. That's basically your schedulers right here. Your scheduler for your data, that's like right here. Scheduler for the data F, and scheduler for the noise, which also has the data scheduler in it. Not sure why, but yeah, basically your signal and your noise. So what is this saying? What is the score? So to break it down, this is basically your gradient with respect to your data. So this is just your data. It's just the gradient with respect to the data. This is your distribution over your data. So given your data, you basically define a distribution around that, and this is just the log probabilities. So it's the gradient with respect to the data of the distribution of the data, basically. Now I'm going to draw that out to show kind of what this may look like. So let's say we have two-dimensional data, x1, x2. Now let's say we have our point here. Maybe this is x0 right here. This is just our data point. And then we define our distribution according to this. So it's some distribution. Now, I'm not going to draw a Gaussian because a Gaussian is not as interesting score-wise. It is multi-dimensionally, just not drawing it out in 2 dimensions, not super interesting. But I'll draw out a different distribution, which kind of gives better intuition for what this may be saying. So I draw this. Now this is kind of like a topographic map-looking thing of your gradient. You can imagine if we just looked at kind of x1, like a slice here, it would be some distribution-looking thing. And this would be kind of like hovering above that, some like some slope, some gradient, some hilly-looking surface above x1, where this is kind of the highest point, and around that it kind of gets lower and lower. And I'll draw this out a little bit wider here. So basically you just define your gradient. So we'll define that as the red arrow. So it'd be like really high here. You have a very high gradient here, magnitude-wise, and it's kind of lower over here. So you're basically defining your gradient along this probability distribution. And this is your probability distribution of x after you apply your normal distribution over it. So kind of adding some variance to it. Giving it a non-deterministic kind of because it's non-deterministic, it was an SDE, so it could take on these values here. Yeah, we'll define a few more trajectories, and these would be kind of longer over here, like that. So this is what score is. This is the gradient with respect to the data, and this is what kind of the score is. Now, why is score useful? Well, you can imagine that, let's say I'm somewhere over here. I can go closer to a high probability, a dense area of the distribution, kind of stepping into a dense probability region of the distribution. In a 1D case, this is easier to see. So imagine I have this distribution here, normal distribution. If I start here, I can step towards the center right here, which is a highly probable area. It's a very highly probable area. So I go from a low density area to a high probability area, like that. And let's say our variance increases over time. If our variance increased over time, then this distribution kind of, I guess, shrinks as time goes to 0. So at time is equal to 0, you kind of have just x0 with no variance. And then as time increases, the variance kind of increases. And as the variance increases, you kind of diffuse out from the center point, from x0. And to reverse the process, you kind of want to diffuse back towards the center. So you kind of want to go back towards the center And that's what this is saying. You actually have a negative sign out in front in the equation. So you're basically going in the, so negative sign right here. So you're basically going up the slope to high probability areas, to dense areas where the data is likely to be at. That's how I kind of look at this. Now, this isn't actually how you do it. You can train a model to directly predict the score, but there's a reformulation where you have it predict the noise, which is nice to have. So this is just reformulation. You go from this formulation here, the score one, the score formulation, and you go to this formulation here with the noise. So basically, there's just they're the same equation. You can just define the score in terms of the noise, and there's a proof for that if you want to see in that paper I showed earlier. So that's the idea. You have your trajectory at some time step. You're changing how you're going to change x, and you are saying it is the current x, and it is your trajectory. So you're basically saying I have x here, and I want to step towards the high probability regions, the dense regions, and your model is basically giving you that. Your model is making this distribution essentially. So, or rather the score. You can get the distribution from the score. So that's the backward process, and those are score models. Now we can finally get to consistency models. So consistency models. I'll have this. More. There we go. Okay, so latent consistency models are easy to get to from normal consistency models. It's as you would expect. But first, let's just start with consistency models. So the self-consistency definition here is basically saying, so if we look at the definition, I'll draw it out over here, like that, epsilon and t, and epsilon you can basically think it's just a small value. So it's like, this is a different epsilon, by the way. This is not epsilon theta, this is epsilon, a small value. So this is like epsilon is equal to 1e negative 4 or something like that. It's basically 0. And basically what this definition is saying, for all t and t prime, you want the values to be equal. So we have this function f, and our function f is saying, at time t, we're going to predict x epsilon, and x epsilon is just x0, basically. So at any time t, our model is going to directly predict x0. So at any time along this trajectory here, I guess it would be going backwards, the model will predict, so maybe right here, the model is going to predict this. And that's an implicit modeling, so it actually predicts the noise, and from the noise you can get x0. But at any time step we have a function f, which is an implicit way of saying our model is predicting x0 at any time step. So we have a time step here, it predicts x0. We have a time step here, it predicts x0, which would probably be somewhere over there. We have a time step here, it would also predict x0, which is also off. So at every time step, we're predicting x0. And yeah, that's some trajectory here. Now, the self-consistency is saying, given f at some time step, and given f at another time step, they should be equal. So if I basically take a time step here, and I take a time step here, then the function here should be equal. So it's basically saying at 2 steps along this trajectory, the values should be equal. Now it says that for every trajectory. So if I just stick with one time step, and then I look at every other time step, so I look at this, and this, so I look at every other time step, then the value should be equal. And I do that for all t. So literally all it's saying is that at any 2 time steps, at every single time step, so every time step along this trajectory, that should be big T, f is equal. So you basically apply this smoothing function. It's basically a smoothing function. At any time t, the value should be the same. So at any time t, the value should be exactly the same as every other time t. And it's just a simple definition of self-consistency. And that's what we want. We want a model that has this. Doing so allows you to kind of skip steps. And in fact, if you had a model that did have self-consistency, like actually did meet the property, then you literally only have to do one step. In reality, you don't actually get that because it doesn't play as nice as you might want it to, the model, but you get close. So that's the idea. Now, first, let's define f. So f theta is going to be x at time, so x, and t, so this is just your unit, and this is going to be equal to c skip. I mean, they have it written down right here. I don't know why I'm writing it out. So they have c skip right here, x, and this is just your data at your current time step, and rather, no, not your data at your current time step. This is just your data. And this is C out, this is your model, and basically this is just your interpolation, so it makes it easy to make a prediction. That's all it is. This is basically your current, so this is your current. Yeah, never mind. So this is your current, it is actually the interpolation. So this is your data at your current time step, your current data, and this is basically your update. This is kind of like dx, or I guess rather, yeah, this is your dx right here. So this is x plus dx, x plus your change in x, and that's just your model. And this should be a one-step prediction, so your dx should be a trajectory that directly goes to x0. So this is equal to x0 or x epsilon. Now, the way they model this is, that's wrong, it's frozen. The way they model this is using this function here. I'm actually going to write it out over here because they define it in kind of a messier way. So basically our loss. So let's assume we have a diffusion model, the diffusion model or a score model, and the score model was trained, maybe it's stable diffusion. Stable diffusion is trained well, it's trained on a bunch of images. Now we basically want to change our diffusion model to be a consistency model. So basically to meet this up here, where at any point the x0 predictions are going to be the same. So we define our loss, and our loss is going to be, well, it's going to be it's going to be a distance function. Well, it's the expected value over x and t, so overall x and t, but it's going to be a distance function. I wonder what this distance function is going to be. Oh wait, it's the L2 norm. Never mind. It's not interesting. Yeah, it's just L2 loss or MSE. Sorry. Whenever they said D, I'm like, oh, they're going to define some weird distance function. It's just MSE. It's always MSE. And yeah, so this is just your data. And instead of using this is basically like a discretized form. I'm going to say x at t plus 1. So this is just x at t plus 1 rather than x sub n plus 1, or t sub n plus 1. I'd rather not say that. Same thing, basically. Minus f theta minus, so specifically this minus here, of x hat phi t and t, just t, and your MSE of that. So this is pretty simple. Now, not looking at this this theta minus, basically all this is saying is, well, actually, let me remove two things. So if I remove the phi and I remove the minus, then basically this is saying at any time step, so at any time step, we want the values to be equal. So if we go here, yeah, and it's the one-step predictions that you want to be equal. If we go back up here, then basically if I have two values, so I say right here and right here, t and t plus 1, yeah, that's right, then I want the one-step predictions to be the same. So here and here are going to be the same. And I do that for all of them. So it's saying the time steps right next to each other should be the same, and I do that for all time steps. And you can see that it basically applies a average or a smoothing function. So as you do this, the function kind of becomes smoother, the trajectory. And it becomes smoother and smoother, and eventually it'll become just a straight line, as smooth as possible. And that's basically, you get to a point where, yeah, it'll be one step where every point along the trajectory is equal to each other, the one-step prediction. In reality, you don't actually get there, though, because optimization isn't perfect. And you may not even be able to get to a perfect one-step trajectory. But they also add two more things. So they add this minus and this phi, or not theta, phi. Phi there. So we have f. F is just your prediction of x0. And this is a one-step prediction using a solver. And it's basically saying your one-step prediction, or this is basically a prediction that was made. And this is basically, yes, this is already a prediction that was made, your one-step prediction using a solver. And your solver discretizes it. So real quick, looking at the solver, you basically have your current value here. You have your discretation, your time step, your dt basically. And this is your solver, basically dx dt. And applying this function, this is basically, like, you can think of it as the trivial Euler case where you just take a step. You have this trajectory here and you just take a step along the trajectory. So your next point would be like right here. So it's just your solver. There's better solvers than Euler, but the Euler case, you basically just you look at the gradient and you take a step or you look at the derivative and you just take a step in that direction. And this is basically your, that's how you actually solve these. You can't solve them because the function is so complicated. But that's what this is here. It's saying your current time step and you're solved. So you're solved. If you apply the solver for one step, that's what this is here. This is your, I have it written down here. It's your one-step estimation that they have it written down here. So you have a prediction of the final step, and your model makes a prediction. And this is actually theta minus. Theta minus, I think that's CMA, but they basically define an exponential. They define an EMA over it. So if we go here, yeah, this is EMA. You basically have an EMA model, and I'm pretty sure this just helps stabilize training, where you have an EMA model and you have a model that's updating. And I think this just stabilizes training, but it's basically like flattening out your trajectories. And I think they just do that in a fancy way because, yeah, this is your updated model, and this model does update. It's your EMA model, so it keeps the model from updating too fast, basically. So I think that's just so that it doesn't diverge as far away from the original model as possible, because you can define a one-step trajectory if you diverge from the original model. So it may not produce a good image, but yeah, I think this is just to help the model out. The core idea is without these, it's flattening the trajectory, flattening the space. So you can potentially make a one-step prediction because it's a flat trajectory. The trajectory that would be the same for all x and for all t. So at any time step, the trajectories, or the one-step prediction trajectory, would be the same. And that's it. It's basically this here. That's how you make it a consistency model. You basically just define it so that it flattens the trajectory, but this also allows room for error. It allows room for error because it basically defines this averaging over the. It defines like you can kind of think of it as an averaging over your trajectory here. It's kind of an averaging in a way. Now you may, whenever I showed this original thing here, where these two are really close to each other, you may see a problem. And the problem is that this is going to be really slow. It's going to be really, really slow because you're just looking at points, pairwise points right next to each other. So I'm going to skip ahead down here. And where was it? No. Right here. So down here, and basically the idea is, well, instead of looking at pairwise, I can actually look, say, here and here. So you define a k, and k is, well, it's not your k, that would be dxk. Yeah, you define a k, and that's basically your maximum time step that you can skip past. So instead of it being pairwise, you just look at a point, say, here, and you basically want to match it up with a point here. And you can see that that would make the smoothing faster. So it flattens out the trajectories faster and way more efficiently than just looking at the pairwise ones that are right next to each other. So yeah, that's an improvement that they make. And now we make this a latent model. So you just make it a latent model by saying, well, instead of looking at the image, we instead look at the latents. And that's all you do. You just define this as a model that looks at the latents, and yeah, this is just z0. Yes. Yes, this is just your prediction here, and you do an implicit prediction by modeling the noise because the noise is easy to model, and this is just your latent. So same exact function, just latent space instead of pixel space. And it's the same exact optimization procedure, except latent space instead of pixel space. And also you can add conditioning. So condition on an image or condition on some text, and that's it. And it's the same thing, basically. And you can also add classifier-free guidance. So if you've seen classifier-free guidance before, we'll move this over. If you've seen classifier-free guidance before, it's pretty easy to add. Basically, if I have a model that predicts the node class and I have a model that predicts a class, or rather I have a model that predicts the noise given the node class here, so given node class, and I have a model that predicts the noise given a class, maybe this is like a dog or a cat, then basically what I'm going to do is emphasize the signal with the class in it and remove the signal with no class in it. So yeah, that's basically what you're doing. You're removing signal with no class in it, and you're emphasizing the signal with class in it. And you can look, if I have, say, w is equal to 0, or I forget what that Greek letter is, but if you have that equal to 0, then you have no null case, and it's just your normal class case. But if you have that greater than 0, then basically you're removing the null class, and it's emphasizing the signal of the class information. If you can kind of visualize that, you have your class information, and you're removing null information that is just general, that wouldn't be adding to the class. It's kind of a trick. Now, this is just redefining your noise prediction, where now you have, I think it's omega, but you now have this classifier-free guidance part, and you just redefine your model and your loss with that part, with your classifier-free guidance part. So the final loss is your model, and it predicts the noise. It basically does a one-step prediction, z sub or z0, given your classifier-free guidance, your class, and your normal time step, and your current noise, or your current latent, so your noisy latent. So that's all it's doing. And this also allows you to pick multiple class signals, so multiple text or multiple omega. So you do an average over all, or you do an expected value over all that. And yeah, down here they define the k, the k jump here, and then they define some solvers as well, if you're curious about those. And if we, and that's the model. That's all it is. It's just it's basically just smoothing out their trajectory. So eventually you'll end up with something like that, something that's smooth. I guess the original curve wasn't very curvy, but if it was, you can imagine like kind of compressing it close to a line, but you don't get a line. It's not completely linear. It's close to linear. So that's what you end up getting. after you optimize this. And remember, you're optimizing off a pre-trained diffusion model. So you train the diffusion model and you're just kind of flattening the trajectory. And it does really good. One step, the FID is looking, it's looking pretty good. These ones totally fail. This one does not. And in 2 steps, it does really, really good. The FID is really low, and it does really, really good at 2 steps. Interestingly, going to 8 steps doesn't do much. 4 steps seems to be the optimal number of steps when sampling with this. And the interesting part is it wasn't trained specifically to do 4 steps. That's just what it ended up being. Ended up getting to a good spot where 4 steps seem to be optimal to go along this trajectory. And stepping along this trajectory, basically you take big steps. So like 1 step would kind of go right here. 2 steps would kind of go right here. And then 3 steps, maybe it goes like right there. And 4 steps like right there. So that's all your prediction's doing. And 4 steps seems to be pretty good, according to their results. And playing around with latent consistency models, you see that 4 steps is actually pretty good. Yeah, so more results. It does well. And yeah, I mean, that's basically it. They define some samplers. DDIM isn't that good. DPM and DPM++ is obviously good, as you probably know. And then yeah, you have to define a range for your classifier for your guidance, and they do 2 to 14, which is a pretty good range. And yeah, that's basically the paper. You're just kind of averaging your trajectories, and that's what you end up with. You end up with a model that can take a step and get some pretty good results. If we look, I mean, this is pretty good. 2 steps, it's looking good. I mean, if you did this with a normal diffusion model, it would not look good at all. You would get complete garbage. But this looks good. So 4 steps, it looks really good. According to their samples. So yeah, it's an interesting model. I thought it would be interesting to talk about since latent or consistency models kind of seem to be doing pretty good. But yeah, that's the paper, latent consistency models.